Hi there. Welcome to the channel where we discuss all things related to actuarial data science. And today we'll be discussing a concept that was brought about a few years ago in 2018, and it's called the Combined Actuarial Neural Net. And there was an editorial, so we'll just go to that paper. And this editorial was published as part of the Aston Bulletin, volume 49, issue 1, and this was published in 2019. And the authors of that editorial are Mario Woodrich and Michael Mertz. Okay, so let's take a deep dive into the editorial. So the authors say, the aim of this editorial is to increase the acceptance of neural net modeling in the actuarial community. Neural nets may substantially improve classical actuarial models if appropriately applied. Right? So, traditionally, actuaries, have the traditional actuarial models like GLM, and they've stuck to that GLM model. It has been working for years. And then came new machine learning techniques. XGBoost came along, neural networks came along that provided an improvement in terms of predictive power. But actuaries have really been slow to adopt these techniques. And this editorial, these authors are then trying to increase the acceptance of neural network modeling, right? And the reason why is that these modeling techniques can substantially improve these models in terms of predictive power, and they can unlock various other things which can be regarded as a good tool that actuaries can use. What the authors then continue to say, well, in order to use combined actuarial neural network, right, there are two assumptions that are critical here. The first assumption is that there exists a sufficiently good classical parametric actuarial model for describing the responses. The parameters of this model can efficiently be estimated with maximum likelihood estimation methods. So basically it says you need to have a model that exists, right? A parametric model that exists. And those parameters need to be estimated using MLE techniques. It should be familiar with the actuaries, MLE techniques, let's park that and be like, you have a model, assumption 1 is met. Assumption 2 then says, embedding of the classical actuarial model in the neural net is feasible. Not too sure what that means. Feasible, could mean maybe hardware. You should have sufficient hardware, enough RAM, CPU, GPU, not too sure. These days, I think anyone can run, small neural network in their laptops. Or maybe the model structure, itself has limitations in terms of ensuring that it can be embedded in a neural network. Not too sure exactly what that means, but, using a GLM, that should be met. Then they say, okay, so once these two assumptions are met, the calibration of neural net uses the classical actuarial model as initial value in the gradient descent algorithm with the deviance loss as objective function. This embedding of the classical actuarial model in the neural net can be interpreted as model blending or as neural net boosting of the actuarial model, right? You're combining both models. It's model blending. You have, for example, a GLM and you have the neural net, right? And you're combining it. But it can also be interpreted as boosting now. So boosting is really, think of it as you have a model that predicts, right? And you have predicted values, and then you calculate your residuals, right? And you can then build a model on top of those residuals, right? And if a model then improves on that, then it means that the first model structure really wasn't sufficient, right? But that process is called boosting. Train a model, you have residuals, train a model on top of those residuals to then improve. So you're kind of like boosting the model. And in this case, you're boosting it with a neural network. And the authors then call this the combined actuarial neural net approach. And yeah, so let's continue. The existence of a classical parametric actuarial model that describes the responses sufficiently accurately is the starting point, right? So like I said, you have that model, it's there, and 2 and 3 aim at challenging this model, right? And then you have defining your deviance loss function. So basically minimizing your deviance loss function is the same as maximizing your likelihood function. And as a toy example, they essentially have a GLM with a regression function, and those of you who are familiar with a generalized linear model, you know that is the regression function. So then they continue to say, in the first step, we describe the classical parametric actuarial model in a first neural net architecture. Okay. Neural nets offer great flexibility, and in most cases, this first step is possible. For our GLM, this is straightforward. We choose one neuron in the output layer with weights beta and an exponential activation function. Okay, so what are the authors saying here? Perhaps it's good to illustrate this. Okay, so let's just say you've got 3 variables, right? So x1 there, you've got x2, and you've got x3. And you really have then one neuron, and this one neuron takes each of those variables as input, right? With beta 0, and then you've got beta 1, and you've got beta 2. And then let's just say you've got beta 0. So in the GLM jargon, it's kind of like the intercept. In machine learning or deep learning jargon, this is called the bias. And yeah, this can mathematically be represented as a linear function of your intercept plus the scalar product of your parameters or weights and your input variables. And all that is remaining then is an activation function. So in this case, it is an exponential activation function, and yeah, then this becomes a GLM that's represented as a neural network, where this neural network just consists of a single neuron. And yeah, then you define your loss function as a deviance loss, so similar to the GLM, and it trains, and what you end up with is a model that is similar to a GLM. Okay, so moving on, the authors then say, in a second step, we choose a second neural net architecture that describes the same regression problem. In our toy example, we assume that this second neural net has 2 hidden layers with hyperbolic tangent activation function and neurons Z1 in the first hidden layer and neurons Z2 in the second hidden layer. This is schematically shown by the following 2 sets of hidden neurons, right? Then you have these, this is the function of the first hidden layer, and then this is the function of the second hidden layer. And basically say that this provides a neural net regression function. So this is kind of like the final then output. So maybe for those of you who are not familiar with neural nets, I will illustrate this. Okay, so let's say we've got 3 variables, x1, x2, and x3. And we start off with our first layer, so layer 1 there. And layer 1 can have any number of neurons, but for this example, we'll just say it has 3 neurons. And each neuron will have the variables as inputs, so similar to the previous example. And yeah, it's kind of like a linear function of the input variables, and then you apply an activation function to it. So the paper mentions a hyperbolic tangent function, but it can be a sigmoid, it can be a ReLU function, as long as it's appropriate. And yeah, what you end up then is an output from neuron 1 of layer 1, and an output of neuron 2 from layer 1, and output from neuron 3 from layer 1. And just by looking at this, you can see that it's kind of like a transformation, right, where you have a new representation now of your input variables. X1 and X2 now becomes Z1, Z2, Z3 of the first layer. And you can see all the interactions. Yeah, and then moving on to layer 2, again you can have any number of neurons, but we'll just stick to the same number, which is 3 neurons there. And each of these neurons will then take the output of layer 1 as inputs into each of the neurons. Yeah, and then this becomes an output from neuron 1 of layer 2, neuron 2 of layer 2, and then the third neuron from layer 2. And really then what is remaining is the final neuron, and this final neuron will then take the output from layer 2 as input into this neuron, and again you have a linear function, right? So this linear function then becomes, so think of it as beta 1, and this is from the third, so this is kind of like the third step, right? Because each of these layers will have, each of these neurons will have their own weights, and it's a linear function of essentially the output of layer 2. And all that is remaining is an activation function. So in this case, it is an exponential activation function. And yeah, so it kind of looks similar to a GLM part. So if you think about our previous example, this portion here is essentially similar to the GLM model that is represented as a neural network with one neuron. And yeah, this is a neural network that the authors has described. And all you need to do is then define the loss function as a deviance loss, and you train your neural net. Like an example in illustration to show you what the authors meant here. Okay, then they say in the last step we blend the two regression functions, right? So we've got the regression function, the GLM regression function, so that's from this first step here, and then you've got the second regression function, which is the neural net regression function from the second step. So then they become blended to then form the CANN, the combined actuarial regression function. So to illustrate this again, so going back to our example here, so it is essentially, so let me just remove this here. So it's essentially, remember in our first step, right? So you've got x1, you've got x2, and you've got x3, and you've got a single neuron there, and those are inputs into this neuron. You've got beta 0, you've got beta 1, beta 2, beta 3, and this becomes your GLM. And this here becomes an input into this final neuron of this let's just zoom out a bit. I don't think this can zoom out, but that's okay. An input into this neuron, right? Which then essentially that becomes plus beta 0, which is from the GLM, then a linear function of all your parameters from the GLM and the input variables. Yeah, so this is essentially what it looks like. This is the combined actuarial network. Then you have a deviance loss function, and you train this model. So just bear in mind that when you fit this as a true neural network, you fit this model first, and then you fix the parameters, so then they become untrainable. But you put that in as a connection into the final neural net. And yeah, so then in simple form, then essentially then this becomes a neural network output there multiplied by the GLM output there, and this is the combined neural network. Okay, so to continue, they essentially say that, you know, they're going to close with remarks, and they essentially say that if the blended model, which is the combined actuarial network model, provides a substantial improvement in the deviance loss, right, then the GLM misses important model structure, and the CANN approach should be used. Otherwise, we should stay with the GLM. So really what they're saying is, you know, if it improves the model, it means that the GLM is missing some stuff. And it could be, like GLM could miss some nonlinear relationships. It could miss some complicated or complex interaction between the variables. But the neural network can handle those very well. And if there exists such a structure in the data, then the CANN should improve on that. But if there's no improvement, then why complicate the model? Just use the GLM. So that's what they're saying there. And if we have a sufficiently good GLM from 1, then we expect fast near conversions of the gradient descent algorithm, because we are already starting the algorithm in a model that is close to optimal. In particular, this implies that bootstrapping of neural nets becomes feasible. Okay, so I mean, if you're fitting a neural network from scratch, right, you don't have any initial value. It really takes a while, it really takes a long time to find a final model. But if you have that GLM output as an initial value, as an input into that model, then that neural network trains quicker. That's what essentially they're saying, because the deviance loss function is almost at a minimum. Then they continue to say, in the gradient descent algorithm described in 3, we may either train beta or declare the initial beta to be untrainable weight. We may also modify the corresponding GLM part. So they're really saying, remember the GLM part, those parameters in the GLM were essentially fixed. So that means they don't change when you're training the neural network, but they don't have to be fixed, they can change, right? You just have to make them trainable. Or you can make them untrainable, up to you. So there's really some flexibility here. And an additional flexibility is essentially then adding a weight, you know, where this weight is trainable and can be interpreted as a credibility weight assigned to the GLM part. Right, so if we go to our example here, where essentially then you can have, let's just pick this here, you can assign a weight here in this addition here that is trainable. where you assign think of it as an alpha here and a 1 minus alpha, right, where alpha is essentially between a 0 and a 1. And yeah, then the model will essentially learn to assign a credibility weight to the GLM or to the neural net. The CANN approach can be applied to a huge variety of classical parametric actuarial models. In particular, we can easily treat categorical covariates using embedding layers in neural nets. Furthermore, the CANN approach even works if we consider several portfolios simultaneously in one blended neural net. This then allows learning across different portfolios. So really, this neural network just allows you to do more things, right? I mean, one additional thing that I can think about is, say you're an actuary, determining premiums for an insurance product, and there are some features that are subject to constraints, right? For example, monotonicity constraints. For example, you want them to be interpretable. There are regulatory constraints. There are commercial constraints, and where those constraints are better dealt with or easily dealt with within the GLM. So you fit them in the GLM. And then the remaining factors that are not really subject to those constraints, you can then fit it in the neural network and then combine the two. And essentially then you have a much more predictive model. That's one other benefit, where you can sort of have a trade-off between something that's explainable, interpretable, subject to constraints, and one way you can just throw it through some very predictive modeling techniques. So that is essentially combined actuarial neural nets. And in the next video, I'm going to show you how to implement this in Python. So do look out for that video. Cheers, till next time.